so people at home, we're going to do another lesson on how carbon bonds are hybridized. And I'll just go over it slowly. I gave you 2 videos yesterday. The one video that is not me, and we watched it in class too, that's a really good video. If you're going to watch something 2 or 3 times, watch that one. That is a really good explanation. I'm going to try to do the same thing with you, just like an assignment I'm about to give you. All right? So first of all, let's talk here. Let me zoom in on the board. Let's talk here about how atoms bond, okay? Now, let's say I've got a carbon atom here. One thing that you know, and it should be written on the top of your periodic table, over carbon, you should have 4 bars like this, right? And if you look up on the table in my room up there, you look real closely over carbon, you can see I've drawn 4 black lines. And you'll see there's 3 over nitrogen, 2 over oxygen, and 1 over the halogens, okay? So these 4 lines mean that carbon is going to make 4 bonds. Every time that you draw a molecule, every time you draw a Lewis structure, and there's a carbon in there, there's going to be 4 lines attached to it, okay? And we label these lines, they're bonds, they're shared electrons. We label these lines as either sigma or pi bonds, okay? Now let's pretend that in the middle of a molecule, there were 2 carbons and they were double bonded, all right? Now you would label the first one sigma and the second one pi, okay? Now sigma bonds, those are hybrid orbitals. That's when an s orbital and a p orbital on a carbon collapse into a new funky shape. It's not a circle like an S. It's not a figure 8 like a P. It's a funky shape, we'll call it a peanut shape, okay? The pi bonds, the secondary bonds, the second and third bonds, those are overlapping p orbitals. Now, I know that sounds like garbage, but let me draw you a picture. You remember we talked about the atomic flower? And I was like, okay, we got that, then we got a bigger circle like that, and then the first P would be a figure 8. The next P would be a figure 8 like this. The next P would be a figure 8 in the Z. You guys remember that? Okay. So let me show you what it really means to be a sigma. A sigma means that this circle and a figure 8 combined, and we don't have a circle, we don't have a figure 8, we make a bond that is like a peanut shape. So a pair of electrons between each carbon is shared, and it's the shape of this orbital is a collapsed s and p orbital together. So it's not a circle, it's not a figure 8, and I'm just going to make up this shape, okay? This is a hybrid bond, okay? That stands for the first dash, okay? Now, the pi, that's the sigma. Now, the pi, which would be the second or third bonds, those would be like if you had a p orbital on this carbon, aren't the p's figure 8 shapes? And a p orbital on this carbon, where they overlap right here. Does that make sense? Those are what the pi's are. That's the only explanation I can give you, okay? So that's what it means. This is how these 2 carbon atoms are being held together. That's it, all right? Now, if you don't understand this, that's fine. It doesn't really matter, to be honest with you. You just need to understand what to do. Let's say we had like a molecule like dicarbon tetrabromine, and we drew it. It means we're going to have 2 carbons And we would end up having 4 bromines like this, okay? I'm going to put all my valence electrons on my bromine. Now they all feel like they have 8, right? Each of these bromines has 3 unbound pairs. And now each of these carbons has 2. Carbons have to have 4. So right in between these 2 guys, bleep, bleep. And that is a good Lewis structure for dicarbon tetrabromide. And I'm sure that there's a name for this that I just don't know, maybe some common name. Okay, now we would label all these bonds. This bond between this carbon and this bromine, sigma, 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 obviously, right? And now let's look at this. This carbon, the first one we'll call a sigma, and the second we'll call a pi. Right? Right? So now let's just talk about this carbon atom. And this one would be the same, but I'm just going to talk about this carbon atom. So if we're going to draw an electron level diagram for this carbon atom, then nothing else matters now. Watch this. We're just thinking about that guy, right? This carbon right here, he has 3 sigma bonds and 1 pi bond, okay? Now what did I tell you a sigma bond was? It's a collapsed s orbital and a p orbital. The sigma is the hybrid orbital. So there are going to be 3 sp bonds, and I told you the pi's are the lapped over p orbitals. So it's going to have 1 p. Now you know what this is going to look like. I'm going the wrong way. Now you know what this is going to look like, okay? Ready? Here is what carbon normally looks like. 1s, 2, 2s, 2, 2p, 2. Correct? Isn't that what carbon normally looks like? But now, this carbon is going to have 3 sigma bonds. So instead of a 2s orbital here, we have what's called an sp orbital here. And there's going to be 3 of them. 1, 2, 3. Up, up, up. The first one is considered the S part of it, and the next ones are considered the P's, okay? So I have S, a P, and a P, all right? And there's 1 pi bond right there. So there's only 1 P that's left over. And that is what this carbon now looks like. 1, 2, 3, 4, 5, 6. This would be called, see how there's an S, a P, and a P? This would be called sp2 hybridized. Does that make sense? All right. If you're at home and you understand, you can stop right now. Do you guys in the classroom want me to work another one? Want me to draw another one, but a little bit faster? Yes or no? Okay, here we go. Let me make up some crazy molecule. How about I got a bunch of H's over here. Got a carbon right there. Got another carbon. We'll throw some F's right there, make it real funky. And then I'll put another H right there. All right? That exists. All right? And I go back. And these guys don't need any, right? right? Let's label all of these bonds. We're going to label all of these bonds. No problem. Sigma, 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 sigma. Everybody's a sigma, right? So if we talk about one of these carbons, we can just talk about this carbon right here. Now nothing else matters. We're talking about this carbon right here. So we don't have to look at anything else in the molecule. We've got a carbon with 4 sigma bonds, right? A sigma bond is an sp hybridized orbital, right? And then a pi is the leftover p orbital, right? There's 4 sigma bonds. Are there any pi bonds? No. So carbon would normally look like this. I'll draw it again. 1s2, 2s2, 2p2. Right? If you don't understand that this is what carbon normally looks like you just lost. Like you need to go back a month in class and get on it, okay? And I don't think that's anybody, all right? So this carbon, since it's been surrounded by other atoms, the orbitals have warped. So they're no longer like this. This carbon no longer has 2 electrons going in a circle in the 2s sublevel and then 2 going into figure 8. That doesn't exist anymore because other atoms around it have forced it to share its electrons, okay? So it's formed 4 hybrid orbitals, okay? So instead of there being 2s and 2p's now, there are 4 hybrid orbitals. The first one we consider to be the hybridized s, and the next 3 are hybridized p. So this would be called sp what? 3 hybridized. Now you'll see me write hybridized sometime with an S. Sometimes you'll see me write hybridized with a Z. This is American English. This is English. Okay? Doesn't matter. That's the whole point. Doesn't matter. 1s2, sp3. That's what you would say when you're reading this. 1s2, sp3. Does that make sense? All right. I'm going to let it roll from there.